Hello everyone, I am Ramashish and I'll give you a brief introduction of this project of recommender system using hash GCN network. So the problem with current GNN models for recommender system is that we get a overwhelming amount of data, and for computing the similarity score between user and between user and items is a computationally tedious task, and it works in a time complexity of somewhere around n into m into k, which is n is the number of users in the space, m is the number of items, and k is the latent representation of everything in the dataset. So the method by which we will be solving this thing is hash codes, and also using XORs to reduce computation by using single bit representation for recommending an item. So there have been a lot of previous work done in this field by using hashnet and hashgnn, where it calculates the Euclidean space between two of the items and two of the users to calculate the similarity. But nevertheless, this task is very computationally tedious and couldn't work for a large model where there are a lot of items. So what we have came out is with a solution that was represented in a paper by uh, Han Liu, which was published in IEEE paper, which is a very recent paper in which they have discovered a new and novel idea of hashing, and using hashing they calculate the similarity score between two users and two items to recommend an item. And this is a code implementation of the same paper. And now my teammates will move ahead and start with the explanation of code and a brief demo of the project. So now I'll give you a demo of the code. So firstly, I'll clone the repository that has our code in it, and I'll run it here in Colab to run it on a GPU instance. I'll get the libraries, and then I'll run the preprocessing.py file to preprocess the data in the format that we want to. And in the model.train.py file, I'll change the max epochs to 20 for now. We can obviously train it for more epochs to get a better result. So as you can see, the model training has started. So now we'll just quickly hop into the code description part, and then we will see the results of the model when it is trained.
We load the data from the pandas, and from the raw data we can see that the dataset contains the movie 100k dataset, and it contains the file, the user item interaction from the user id, movie id, and the rating in the scale of 1 to 5. And after that we count the number of triplets of the data, and we store the user id and the item id, and from that we count the total number of users and the total number of items and the total number of interactions, which is nearly 100k. After performing the train and the test split, we create the train and the test arrays, and after that we add edges to it, and we create a one-hot encoding containing the train matrix and the test matrix. And from here we save the data into a external file movieload.para, and we load it to form our triplets for training. We calculate the number of users, number of items, and we keep a negative sampling ratio of 5. From there we create a matrix of the dense matrix of the train matrix, and from there we generate our training triplets, and we keep it into 3 training triplets, and then we move on to the training part.
In the training portion, first of all, we load the data used for training our model and access the total number of users and items. Here we are defining users and items, and then we also find the edge indexes and the number of node features that we want to have for each particular node. Over here we are defining the forward and backward functions in the class, which basically returns the sign of the elements of input vectors during forward propagation and restricts the values from -1 to 1 during back propagation to prevent overshooting. Over here we are defining the model architecture using the HSGCN modules. That the architecture basically takes as input the node feature matrix and the graph connectivity info vector. The node feature matrix is then passed to the tan activation function, followed by applying the forward and backward methods if we are training. The data is then passed two times through the HSGCN blocks, followed by a dropout for regularization. Here we have passed the model and our data to the GPU or CPU which we are using, and then defined the learning rate optimizer and other parameters that are required for training. Over here we are basically loading and constructing a data set which we had earlier stored in different blocks, which is then sent inside the training loop. The model basically gives as output the learned embeddings along with the initial embeddings. Then we extract and aggregate the model outputs for each step and calculate the predicted vectors and get the binary cross entropy loss for the batch. We also calculated the rank loss using our predicted values, which have been used for construction of the final loss function. The rank loss basically helps us check if the recommendations made have been made in the preferred order or not. And the final loss is the summation of the cross entropy loss and the weighted rank losses. And for the testing of the model, we follow a similar approach as used for training. For evaluation, we make 50 recommendations for the user and test the same. We get the train and test matrices along with their hash codes, and for evaluation, we are calculating the hit rate, the number, which is the number of times we make the correct predictions, the probability of the number of times the recommendation is provided in correct order, and the normalized discounted cumulative gain, which is basically a metric of how good is the recommend order of the recommendations that we made. And in the evaluation loop, we get the IDs of all the movies the user has watched and get the hash codes for the same, and sort the item IDs. And for each user, we calculated the discounted cumulative gain for each item, which is later normalized. And these are the basically what we give as output for evaluation of a model.
So as we can see, the model has almost finished training, and the loss has also come down from 1.08 to 0.4, and the decrease of loss has almost gone constant. So we will stop training here and we will move to the testing part. So this is the metric that we have learned, and now we will test it. So this is the result that we have got. The HR50 is 0.10, NDCZ is 0.16, and P at the rate 50 is 0.10. So these metrics are for 50 predictions that we have asked the model to, and we have scored them on different metrics. First is the probability, then the hit ratio, and NDCZ.